Have you ever wondered how the Face ID on your phone is exactly able to recognize you and not your cat? Or how Amazon recommends the exact same phone cover that you've been looking for all week? Is there a secret sauce? Amazon processes over 600 million packages every year. And behind every recommendation, there is a smart algorithm called Support Vector. Hello everyone and welcome back to my YouTube channel. I'm Selina, and in this week's video we are going to discuss the intuition behind support vector, which is one step ahead of linear regression that we studied about in the previous video. We will understand how a few crucial points called support vectors help make huge recommendations within a large set of complex data points. We will do this by understanding the origin of support vectors, how they are different from linear regression, and what makes them so special. We will ask more and more difficult questions until we have understood the entire topic in great depth. So let's jump right in. Let us now understand the definition and history of support vector machines with this simple example. So imagine you are at a picnic with your friends. On one side you have sandwich lovers and on the other side you have salad fans. And you want to divide these two groups, otherwise they'll start fighting. And for that you need to make a single line. So how will you do it? Well, back in 1963, two amazing scientists, Vladimir Vapnik and Alexei Chernonkis, decided of something new, something that they came up with to divide these two groups of people, or let's say data points. They came up with this incredible idea of support vector machines, wherein this was used to not only divide the people into two groups but leave the maximum margin between them. And this was called the maximum margin principle. The key players here are the support vectors, or the friends that are closest to the line. And why are they so important? Well, because if they change, or well, if they move, then the whole line will change and the maximum margin between the two groups will change, and it will affect the line that we are separating them by with. So when a new person joins the group, we will decide if they are more of a sandwich person or a salad person based on these support vectors, or the friends who are closest to the line. Let us break down the graph of this SVM and its key components step by step. Firstly, we have the data points. On the graph, you'll have two classes of data points represented as dots or circles, and the other as squares. Next, we have the hyperplane. The hyperplane is the central component in an SVM graph. It is essentially the line that separates the two classes of data. As you can see over here, it is this dotted line. Support vectors. The support vectors are the critical data points. Over here, the three circled using dotted lines. These points support the hyperplane by defining its position and orientation. Without these, the boundary could shift. So if these squares would go any further, then the boundary would shift further, and so will this hyperplane. And the same situation will arise if this dot moves to the right or to the left. The margin would shift and the boundary would also shift. Margin. The margin is the distance between the hyperplane and the nearest data points from each class. Over here, as you can see, this is the margin, the distance between this dotted line and the line that is formed when we cut through these squares. Classes. These are the distinct groups in the data set you are trying to classify. In our example, it is squares and circles. The whole purpose of support vector machine is to separate these classes as clearly as possible using the hyperplane and the margin. Support vector machines do an incredible job when it is linearly separable data. That is, we have data points that can be separated by a single straight line. But what if we have data that cannot be separated by a single line, or we cannot represent it by a single mathematical function like this? So then what will we do? To solve this problem, we use a technique called kernel trick, wherein if we are in 2 dimension, we increase the dimension by 1 and go to 3 dimension. Once we are in this 3 dimension world, we can separate the points by something called as a hyperplane. But what are kernels and how are they used? So basically, when you are going from a lower dimension to a higher dimension, say from 2D to 3D, you want to know what will be the coordinate of a point which was once in 2D space in the 3D space. Now we cannot sit and calculate every single one manually. So for that we use functions, and these functions are called kernels. Say for example, my point in 2D space is 2, 1. Using a function like RBF or polynomial function, which are essentially kernels, I will get to know the position of this point 2, 1 in 3D space. Now, what are the two main goals of SVMs or support vector machines? Well, firstly, it is to create the maximum margin between the two type of classes that we are trying to separate. And second is to classify as many new inputs correctly as is possible. So let's say there are cats and dogs. You don't want to mistake the cats for the dogs. That is minimizing the error. And the second thing is you want to find the best line that separates the cats from the dogs. So these are the two main goals of SVM. And there is one parameter that helps us achieve this, and it is called the C parameter or the regularization parameter. It is like a trade-off. So to understand this, let us take the example of a seesaw. On one hand, if you increase the C value, that is you make it super large, then you will be able to reduce the errors. Maybe every single cat and every single dog will be classified properly, but then your margin will reduce and maybe it will shrink to a single line, and this is known as overfitting, wherein everything in the training data is classified properly, but when you put in some new testing data, then the model is not able to understand where it will go and how you will classify it. On the other hand, if you reduce the C value, you will be able to increase the margin. But then what will happen is some of the dogs will be misclassified as cat and some of the cats will be misclassified as dog, because the margin will increase and it will engulf all of the wrong findings as well. So you have to find the optimized solution or the correct value of C that balances both of them perfectly. How do you evaluate a support vector machine? For that, there can be multiple techniques, and some of the metrics that are used are accuracy, precision, recall, and F1 score. Another idea is to use a confusion matrix, which gives a more in-depth analysis of how the classes were classified using the support vector machine. In conclusion, support vector machines are one of the most powerful machine learning algorithms that use a few critical data points to make the most informed classifications. Be it email filtering, image recognition, or even predicting customer behavior, support vector machines are everywhere. That was all for this week's video. I hope you enjoyed it, and if you did, then don't forget to like, share, and subscribe. I'll see you again in the next week with another new algorithm and the intuition behind it. Till then, thank you for watching and see you later.